Okay, so share my desktop one more time. Okay. All right. Well, gonna get started today. So what I plan to do today is to do three things. One is to finish off this lecture on elements of inferential statistics, chapter 9 of the book, and I've updated the slideshow, just one slide in the slideshow, because I realized that there was an error. And so you won't see this one anymore. This is the old one. So this is the new one. If you want to go ahead and download that and delete the old one, you can. So that's one thing that we're going to do. And then the second thing that I want to do is do this lecture 10. And inside lecture 10 is the third thing that I want to do is review for the test that's next week. And remember that it's open. It's open book, and I want to answer any questions that people have regarding it. And even though it's open book, there won't be tons of there are going to be some calculations, but we'll talk about what that is. Okay, so we'll do that in that order, and we'll talk a little bit about strategies for tackling the homework that's coming that's in each of these two chapters. Now the test actually won't cover what we're going to talk about today. The test won't cover this, the two sample part. So the test will stop here. But really, what we're covering here in week 9 or week 5, which is chapter 9, really that concept will be like repeated throughout the course. So we're going to be talking about doing some sort of statistical test each week, and there'll be a few more things to look at besides just whether the test was successful or not, the hypothesis test was successful or not. But it starts off with just look. That's the goal, is to find out if the hypothesis test was right or not, but also to formulate the hypothesis test right. So anyway, on that note, let's actually talk about the slide that I updated. So I noticed that this slide didn't match the book completely correctly, and so I updated it. So this slide now matches the book, and it was actually mistyped before. So I had something like I think I had these two combined or something like that. Anyway, I forgot exactly what it looked like, but this matches the book. So we're going to walk through each of these, because this concept right here is actually really important. It's more important than actually calculating out the numbers, because from now on, pretty much almost exclusively, there might be some like data wrangling to get the table to look the way that whatever software you're going to use to run the test wants the data in. And sometimes the software we're going to use is a GIS software package. A lot of these will work in Excel, but not all of them. Particularly today, I mean, I'll show you that. And then we are going to have to like return back to Python a little bit, but it's like now that we're actually running tests in Python, we're not doing data wrangling. Because before I was trying, like, I was calculating weighted mean. I was trying to like do data wrangling, right? So I was trying to like, you have to multiply every value by the weight, you have to add them all up, and you divide by, right? So now that we're actually running tests, it's more like column A and column B contain my data. Run the line of code that actually performs the test that we want, and then interpret the results. So you'll see that's why this here is actually more important than the math at this point. So what we want to do is we're going to follow this through for a number of different things. At first, just general hypothesis tests, and then well, actually, today's subject, chapter 10, is just general hypothesis test. Chapter 11, too, is a little bit a little bit more general hypothesis tests. But then after that point, we start talking about spatial ones, and that's where we'll get into some of the GIS software. All right, so for each one, we have to understand for a specific test, there's a specific null and alternative hypothesis. So however we're coming at it, the first task is to state the null and the alternative hypothesis. And then identify the appropriate statistical test. These are almost like grouped together, okay? The statistical test that you choose will have an impact on what the null and alternative hypotheses are, and vice versa. The null and alternative hypothesis that you choose will help you determine what the appropriate statistical test is, these two things. So as we talk about different statistical tests, you'll see what the general null and alternative hypotheses are for those tests. Okay, and then step 4 is true no matter what. For any, you always have to do step 3. You have to select the level of significance. In other words, this is one of the things we covered last week. You're choosing what type, how comfortable you are making a type 1 error. In other words, it being not true when it in fact is true. So if you want to be right in 90% of the times that you would collect your data and perform a sample like this, then you need to choose a 90% significance level. Or if you 95, or you almost never want to be wrong, you should say 99, or maybe even more. Okay. You just have to realize that as you do that, your confidence interval, which will have an effect on whether or not you accept or reject that hypothesis, gets bigger as your level of significance increases. All right, so once you choose your level of significance, you can go ahead and delineate the regions of rejection and non-rejection of the null hypothesis. So this is really important, but only in the sense that you're choosing here whether or not you actually chose it up here and you formed your null and your alternative hypothesis. Here you're just delineating it. So we'll see here on the slides that basically what you're doing is you're deciding whether or not your test is going to be one-tailed or two-tailed, right? So if it's one-tailed, you're only concerned with probabilities associated in one end of the tail. It's two-tailed, you're concerned with it in both. And we'll see how that plays into it when we go through. Now, step 5 is the step that oftentimes gets done like really quickly, and that's why I'm saying that calculating these things at this point, we're not doing data wrangling. When we come up with a little bit of data wrangling sometimes to get the table in the right format, but we're basically just calculating the test statistic that we decided that we wanted to calculate up here. So oftentimes software aids us in that process, and at the end, the software is going to spit out sometimes it spits out the test statistic itself, but sometimes we don't even really care about what the test statistic is. In other words, if we're doing a normal distribution, it'll stick out a z-score, and if we understand the normal distribution and we get a z-score, we can tell how many standard deviations it is away from the mean. But what we're really interested in almost always is what's the area under the curve. In other words, what's the probability that we would be making a mistake if we chose to accept the null hypothesis, or it's the opposite of that probability. It's 1 minus that probability. That's what we call the p-value. The p-value, when it is really, really small, then we're, in almost all cases, with these statistical tests we're going to talk about today, when the p-value gets small enough, we can be comfortable enough rejecting the null hypothesis when the p-value gets small. And so it's the probability that the opposite of that is because it's always a really small number. The opposite of that approach is 1, and that's the probability that we're not making a mistake there. All right, so then we need to know how to take that and compare it to the level of significance. And really, you could argue, well, why don't I just find out what the p-value is and find out if I'm comfortable with that error? Well, you can do that, but that's ideally you should decide beforehand what your cutoff is. Okay? If you're really truly doing a hypothesis test, you're not saying, well, I could live with that, and then accepting or rejecting that value. So you have to make this decision whether or not your null or alternative hypothesis is by looking at the p-value that comes from the test, and that's the area under the curve. So the test statistic is the value along the distribution function, and then the p-value is the area under the curve. And so you can compare that to your level of 1 minus your level of significance. Okay, so we talked about this. So every statistical test that we talk about after this point will have a null hypothesis associated with it. So in this case, what we're going to talk about today is just the general form. It specifies that a hypothesis value for one or more of the population parameters. So we're talking about a sample, so it specifies that one or more of those values matches some population parameter. And then the alternative hypothesis is always something that the population parameter is something other than the value specified by the null hypothesis. Typically, it's greater than or less than. Okay? So we're either saying the null hypothesis says that some parameter is equal to it, or that two samples, the differences is 0, and then the alternative is they either don't equal 0, they don't equal each other, or they are greater than or less than. Okay. So hypotheses, they're mutually exclusive. Only one could be true. That's an important distinction between the null and the alternative hypothesis. Basically, another way to say this, like in computer science, would be the null hypothesis is a statement that things are equal, and then the alternative hypothesis is that they're equal, greater than, or less than, and then the alternative is not that. Okay. So we can have two different forms of hypotheses. One is that they're equal, and then the alternative hypothesis would be that they're not equal. Another one is that it's greater than or less than. So an example of this would be if I ran an experiment and I wanted to basically, well, I just saw your poster about yard signs, right, in the back. Mm-hmm. I didn't actually read it all, but I got that. So I gathered there was something where you went around and looked at yard signs before an election, right? Okay. So if I could get the election data after it happened for a particular area, whatever that is, a whole county or just a voting district, and I knew for certainty what the proportion was between who voted for candidate A and who voted for candidate B, right? So I would have that, and I could call those my population parameters because I actually have, and my population wouldn't be every person, but it would be voters, right? So I would actually have the population data, and if I, just before the election, I'd driven around and done a yard sign thing beforehand, I could hypothesize that either candidate A or candidate B had a greater proportion, an overrepresentation of yard signs. In other words, they were more vigorous in their yard sign planting, because what I'd be doing is I'm inferring that people that put a yard sign out are going to vote for that person, right? Like, which is not, I mean, it's not a weird assumption. So in that case, if I could either say as my hypothesis that the ratio of yard signs should be equal to the ratio of actual votes in that particular area. And I could test that hypothesis. Are those the same population? In other words, do people put out yard signs at the same rate as they actually vote? And that'd probably be interesting because and we wouldn't expect a one-to-one relationship because we know not everybody that votes puts out a yard sign. But it might be interesting to know if one candidate was more likely to do that. Now, if I actually had noticed one candidate's voters putting out more yard signs, I might hypothesize that that their proportion would be greater than the actual proportion. So that would be a one-sided test versus a two-sided test. And what that allows me to do is to be a little bit more confident. You'll see that when we draw the things, but there is a distinction between one-sided and two-sided tests here. Okay, this we did talk about a little bit last time, but we're basically looking so that our confidence level, like our significance level, is this PR. So PR is equal to 1 minus alpha. Alpha is the opposite, the leftover. Okay, that's what we're going to compare to the p-value that we get. So p and alpha will get compared. And basically, if p is less than alpha, then we're going to reject and go over here. If p is greater than alpha, we're gonna accept the null hypothesis.
You said alpha was the error, right?
Alpha is just is 1 minus the significance level that we're comfortable with. In other words, we want to be right 95% of the time. We would do a sample like this, and so the alpha is going to be 5%, the leftover. Okay, and so if we run it, and in other words, if we run it and let's say in this scenario we have 0.5 or 0.05 as our alpha because we said we want to be right 95% of the time. Okay. When we run it, the p-value is telling us if the null hypothesis really is true and you ran a sample, you'd only expect to get this weird of a difference or this strange of a difference this percent of the time. So if our p-value turns out to be 0.03, in other words, we could collect another 100 samples and only 3 of them would show you this result. And so that's why we could say, well, it's not very likely that we collected that one of those 3 weird samples. It's more likely that we collected one of the 97 good samples, so therefore we're going to assume that we're over here. Okay. But if it was 0.12, in other words 12%, then what we're doing is we're saying, well, could have been that we made a mistake. So we're going to accept that null hypothesis, even though we're looking at we'd only expect to see it this weird 12 out of 100 times. So that's really what we're saying. Okay.
Rejected it. Are the p-values bigger than the alpha?
No, the p-value is less than the alpha.
Okay.
If we reject. If it's really small, then there's a very small chance that we would have. In other words, if our null hypothesis was true, there's a very small chance that our sample would have produced this. So it is true that um, your you should make your null hypothesis should be the one that you think is correct, the one that you want to hold on to, because that's the one that is mounting the bigger problem, or the bigger. It's harder to reject it. I mean, we gotta have a small significance level to reject it. All right, so the next thing that was on the list was to select a statistical test. Now, so far, we are just up here in this one sample z-test, a one sample t-test, which really the difference between these two is simply that you have enough samples. And they're almost identical once you have more than 30 samples. So it really, in Excel, just always use this t-test in Python, because it will be the same once you get over 30 samples. They'll be really, really similar. Okay. All right. And then we have this one proportion z-test. Okay, now this one is probably, well, this one we can't, there's no tool for doing this in Excel or Python, because this looks kind of scary, but it's really not that scary. We're just taking the proportion that we sampled, the sample proportion, minus what we think the real proportion should be. In other words, just a real simple version of this is that we would go flip a coin 100 times. And if we got 80 heads and 20 tails, we could think, whoa, that's weird. That shouldn't happen. Could that have ever happened? What's the probability that would happen? Well, we could compare 0.8 to the difference here would be 0.5, the population proportion, because a normal coin should be 50-50. And then we could divide that by this is p, or 1 minus p, and that's the population. So it's 0.5 times 0.5, which is 0.25, divided by n, which is 100. Right? We did it 100 times, and we take the square root of that. So it's pretty simple, and that'll give us a z-score. We can go look that up either in the z-tables, or we can use Excel to look that up, and we can figure out how weird is it that we got that. And in this case, probably our null and our alternative hypotheses would be what? What would be the null hypothesis in this? Like, why would we even test this? Let's come up with an English language way to express the null hypothesis. The null hypothesis here is, the general null hypothesis is that our sample proportion is equal to the population proportion. So what would be a way to say that for the coin flipping?
A normal coin should result in a 50% probability rate?
Right. So another way to say that is this coin weighted somehow? Is it's got something that's causing it not to be normal, right? And so our null hypothesis is that they're equal, but what we're actually trying to test is if this coin really doesn't have anything wrong with it, what's the probability that we would have gotten this weird 80-20 ratio? Okay. And so, like, we could, by the way, I copied and pasted that from I think from Wikipedia. I put the slide on there, but yeah, it's in table 8.4. It is the no, sorry, that's the confidence interval, but it's very similar to that formula, because that one's just the confidence interval for the proportion, and now we're talking about yeah. So it's in table 9.6. It's the bottom one. P, and here they don't use p. I like p hat better. They use cursive p versus a normal p, and then they show each one. Okay. Then yeah. So if we were to just do this really quick in Excel, I mean, you could do it in a calculator, but I'm just going to say equals 0.8 minus 0.5. That's the numerator. And then the denominator is the square root of 0.5 times 1 minus 0.5, which we know is going to be the same as 0.5, divided by 100. And I'm going to put this all in parentheses. That's right. And then equals this divided by that. We get 6. That's the z-score is 6. So at this point, when I have a z-score of 6, does anybody know what's the area under the curve going to be? Just like, is it going to be big or really, really small? Remember, the z-score is in standard deviations from the normal, the standard normal curve, which has a mean of 0 and a standard deviation of 1. So it's in standard deviations.
That's a lot of areas.
Well, which way are you thinking of the curve?
Like if you do 6 standard deviations out, that'd be a lot of area underneath the curve.
Right. Okay, so it's a lot of, you're right. So if you go 6 over, there's a lot of area left under the curve, right? But what we're actually concerned with, the p-value, is what's left on the other side, the tail. Yeah. And so it's like infinitesimal amount, right? And we don't even need to calculate. We know that's weird, but we can calculate it by just it's normal to find out the area under the curve. We would say normal so normal returns the normal distribution, returns the inverse. I always forget which one's which, but so we want the standard normal. The mean is 1. Sorry, the mean is 0. The standard, the x is, sorry, this value. And then 0, 1, and we want it cumulative, true. So that Ashley's right, that's basically the whole thing. And then I don't know if at 6 there's really nothing left, right? There's nothing left out there. So it's just too small to even measure in Excel.
2 standard deviations, 98 usually.
2 standard deviations is 90, almost, yeah, 98. 3 standard deviations is a little over 99. So 6 standard deviations. You know, think of that curve. Here, I'll bring up PowerPoint. So that curve that's going out here, 6 standard deviations out, is like way out here. Okay. Now, not every time we're using the normal distribution, but a lot of times we are using the normal distribution. But every time we do it, there's a distribution function that looks like this. And as you get further away, as the test statistic gets higher, no matter what, as the test statistic gets higher, your p-value gets smaller and smaller. Okay. All right. So that kind of walks through that process. Now, just for fun, if we change this to 0.5, what should happen? In other words, well, let's change it to 0.51. Let's say we flipped it 100 times and we got 51, and we wanted to see what's the probability that would happen. Well, oh yeah, we need to also update. Oh, that's the only time it appears. What is it? Oh, because I made that. This divided by that. Now that's just barely So the mean should be 0 on the standard normal curve. So the standard deviation is only 0.2. So the probability, we would expect that to happen almost 60% of the time, that it's either that or close to 50, almost 60% of the time. So with this p-value, this is basically this isn't the p-value. The p-value would be 1 minus this. So that'd be the p-value. With that p-value, should we reject or accept our null hypothesis? In other words, when we reset this to 51 out of 50, I mean 51 out of 100 instead of 50 out of 50, we're saying, are they equal? I mean, could this really be a normal coin, or is this some special coin? Well, the null hypothesis is that this is just a normal coin. You see how when that value gets over our threshold of 0.5, I forgot to set I didn't set a significance level, but if I had, now that's over it, so what do we need to do? This time we need to accept the null hypothesis. So it is a normal coin.
Okay.
See what I'm saying? The other one is not a normal coin. So we need the null hypothesis is that the two flips were equal.
Okay.
Not the two flips, the equal compared to the overall. The flips compared to what it should ideally be. Yeah. So I think that brings another question in here, is for each of these, the ones that say 1 next to them, one sample, that's what's covered in chapter 9. In each of these, the test that you're testing is, I know something about the real way it should be, or there's a theoretical real value, and I'm testing whether or not my sample matches that theoretical value or that real value that I got. So in the fake scenario I just came up with, we test it the exact same way. In other words, let's say Donald Trump got 40% of the vote in a particular area. 40% of the vote would be the. Oh, here, let's go through the whole thing. Okay, so our thing is that the proportion of yard signs is different than the actual vote. Okay, that's what we're going to do. The proportion of yard signs is different than the actual vote.
That would be the null hypothesis?
That's the null hypothesis is that they're the same. So the null hypothesis is you're right, I should have stated it like that. The null hypothesis is always that they're the same. The alternative hypothesis is usually the one that changes. The null hypothesis is either greater than, less than, or different. See what I'm saying? That's why sometimes I'm in the habit of expressing the alternative hypothesis first. Okay? All right. So let's make this bigger for the folks up in Hattiesburg. View. I don't know why that's not letting me make it bigger.
You can do it down there in the phone, huh?
We can see it.
You can see it? Okay. All right. So that's the null and the alternative hypothesis. Okay? Is that the proportion of yard signs is equal to the amount, in other words, the yard signs are a surrogate for how the vote's really going to turn out. That's another way to say it. The yard signs should be representative of what turns out. I mean, we're kind of testing whether that's a safe assumption, right? Okay. So that's the alternative hypothesis, is that those proportions are equal. Okay. So in order to test that hypothesis, we need to come up with, we need to find out what the proportion was. So let's say for this last election, Donald Trump got 40% of the vote in a certain area, but I don't know, what do you want to test? How many yard signs might he have gotten? Just pull a number out.
150.
150 out of how many though?
Like 60%?
What's that?
1,000 residents.
Okay, 150 out of 1,000. Okay, so you wouldn't do residents. So It'd be 150 out of
Household.
the total number of signs. It's a proportion of the signs, right?
Okay. So not proportion of the hundreds.
Well, it depends on what you want to test. So if you want to, like, there's a lot of people who don't put out yard signs, right? Then there's also lots of people who don't vote. But what we got at the end was just the people that voted.
Okay.
So, I mean, it depends on what you want to test, but I think it makes more sense. The proportion of yard signs should be similar to the way that the votes shook out.
So out of 500 yard signs, 200 of them were Trump.
Okay, so 200 were Trump, so 2 out of 5.
Yeah.
Okay, so that would go here. So let's do 200 out of 500 minus, and we're going to say that in reality, 0.4 people vote. When we went and tallied it up. In fact, we could actually do that as let's say there were 400 people that voted. So this shows how data wrangling stuff. Okay, 400 out of 1,000 people. This is a weird census tract where exactly 1,000 people voted, or weird voting district. So here we have the number of yard signs, the total number of yard signs, the number of Trump yard signs, the Trump voters, and the total number of voters. So those are the ways we form those two proportions. So whatever question you're asking, you can form them in a similar way. And then okay, those are exactly the same, are they not? Yeah, they are. So we should ideally get, well, we're going to get 0.5. We should adjust this because this is now, 0. In fact, if we wanted to do this right, I think what we should do is test so yard signs. Let's do this like this. Yard signs Trump. Total signs. And then votes for Trump. Total voters. 200, 400, 400, 1,000. And then this would equal, here, let's just calculate beforehand. 200 divided by 600 equals this divided by that. Okay, those are different, sorry. So this will work out fine. So equals this minus this is the numerator in that formula. And then the denominator, instead of this, we're going to do this one and this one. So we get that value. Okay.
They're both supposed to be the 0.4 on the bottom?
What's that?
As a formula, they're both supposed to be the 0.4 on the bottom?
Oh, wait, you said this one was 500 before, but anyway, what's that?
Oh, I just, on the formula to figure out your 0.4899.
Yes, they're both supposed to be 0.4. If you look at the formula, it's kind of hard to see, but I'll zoom in here. You can see that it's just the population proportion times 1 minus the population proportion. So what we're doing is we're saying this. Well, first of all, that's the p-value that we get. That's the p-value. This is the test statistic, and in this case, it represents standard deviations from the normal distribution, which 0 is the mean. So it's 2 standard deviations over. So in this case, if this really was the yard sign ratio, and these were and this really was the voting ratio, we get a ratio of 0.5 to 0.4. Those have a difference of 0.1, and then this is the standard error of that difference. And then we would get this test statistic, and the important thing is looking at this number here and deciding whether or not to to say these are equal or not. To accept that they probably are equal is what it means, or to say, oh no, those are definitely not equal. And in this case, what would we do? Would we say that they probably are equal? Well, if this number is bigger than our confidence level, we didn't decide on a confidence level, but let's just say it's 0.5, then we say that they are equal. If not, we reject it and say that they aren't equal.
That wouldn't happen, like that scenario wouldn't happen like 0.02 of the time. Like
right. With
2%
that,
of the time, it wouldn't happen that way.
right.
Okay, so it's saying we're 98% sure that the sign would predict the voting.
Yes. Another way to say that is that the confidence interval that we construct, if we constructed a confidence interval, going back to chapter 8, we constructed a confidence interval, and we did this survey thousands of times or hundreds of times, it would only include that value 2% of the time. In other words, the 0.4 and 0.5 would only include themselves 0.2% of the time. So we reject the null hypothesis. These are not equal. That's what we would say. Now, if we did make this 500 again, like you said, see how that goes? And now it's 0.5, and that's much greater than 0.05. So what if it was, 136? Well, we can test that. Now that's bigger. I mean, that's really big, right?
So this is testing to see if they're like a 1-for-1 match, not necessarily like they're in the same direction, like
Yes. So this is just testing whether or not they. This is just testing whether or not they are different. Now, if we want, we are going to talk about that in a second. Okay. So it said if we only want to have a 5% possibility of rejecting HO if it's really true, say our significance level is 0.5. We covered that. Now, we do need to think about how that goes in, because so far what I've covered is it different? And when it's different, we call that a two-tailed test. And we're testing the middle of this curve, and so we actually divide our confidence interval in half. And if we're doing a one-tailed test, we're only going to consider, in other words, we know that it's not going to be down here, and so we don't have to divide our confidence level in half. We can put it all on one tail. So actually, what I was testing is a one-tailed, because I didn't divide our confidence interval in half. Okay. Yeah, I didn't divide that value at the end, the p-value. Not the p-value, the rejection criteria. I didn't divide that in half. So if you want to be right 95% of the time, then what you'll do is take 95, subtract it from 1, you'll get a number. What number is that? 95. 1 minus 95. 0.5 or 0.05, right?
Yeah, 0.05.
0.05. And if you want to test whether or not it's different, you'll divide that number again by half. And that'll be your cutoff. So it'll be 0.25 if it's 5. Okay, that'll be your cutoff. In other words, if your p-value is bigger than that, accept the null. If your p-value is less than that, reject the null. However, if it's one-sided, then you could just assume this is never going to happen. In other words, and you could put all of the likelihood onto one side, and so you can keep that 0.5 cutoff. In other words, you can be confident that you're going to be right still 95% of the time because you're confident that it's not going that way, or it's not going that way, either way. So most statistical software will give you the p-value. In other words, it'll give you the area under the curve, whether it's like a small area like this, or whether it's a big area that goes all the way over here. It'll give you that area. And so if that number is smaller than your cutoff, you're good, and you reject the null hypothesis. If the number is bigger, you're like, oh well, it's bigger, it's probably likely that they're the same. And so the words on here, likely means likely that the null hypothesis is true, unlikely that the null hypothesis is true. That's what the words represent there. Okay. All right, so you're always going to be calculating your test statistic for all the ones that we talked about, that we're going to talk about in this chapter. It's either a Z or a T test statistic, which are both either the normal distribution or very similar to the normal distribution. So once you get a p-value, you compare it and you make a decision. You decide to reject or accept the alternative hypothesis. Okay. So just remember, the only real hard thing, once you kind of like get into the pattern of doing this, because what's going to happen is you need to do some data wrangling sometimes to get your data into the test. But then the test will be performed using software, and you get a p-value. And the only real kind of thing to think about is, okay, I've got a p-value. What does that mean for my null and alternative hypotheses? And the only real thing to think about there is whether or not it's a one-tailed or a two-tailed hypotheses test. Okay. And if it's a one or two-tailed hypothesis, you just need to either, there are some people that double the alpha value and leave the cutoff value the same. There's some people that double the p-value. You could double either one. I like to do it the way I described it here. Sorry, half the alpha value rather than double the p-value. But you can do either one, because you're going to get the area under the curve. Sometimes, though, depending on the test you do, they'll give you the option to double the p-value or half it in the code that you run it. So you always have to be aware of what you're getting as the result. Here, we're doing it all manually, so we can think about what's coming back. Here we get a value of 0.002. We know that it's way up there, and that value that we're getting is way up on the edge, and we know that we're doing whether we did a two-tailed, so our cutoff values would be 0.05 or 0.025 for a two-tailed. Is this greater or less than any of these? Is this number greater than that number? Mm-mm. This number right here, is it greater than that number?
Yeah. Sorry.
Yeah. Is this number greater than that number?
Yeah.
So it really doesn't matter in this case whether we're doing a one-tailed or a two-tailed test. But let's just say we were saying the number of Trump yard signs is greater than the proportion. That was our null hypothesis. The number of yard signs is equal to, and then the alternative hypothesis was the number of yard signs is greater, the proportion of yard signs is greater than the actual voter turnout. Okay. So in this case, we would say that
this wouldn't be an outlier, this area of voting or this voting district. It wouldn't be unheard of.
Well, what we're doing is testing whether or not this is a real sample of this population. So this is not a representative sample of this population. We're rejecting the null hypothesis that these two proportions are near each other. In fact, well, this is 100. I should actually change, because that's not always 100. That's always n, and n is this value, the sample size. So that changed a bit. In fact, now it's like microscopic. I made a mistake earlier assuming that everybody knows. So Excel actually, when the number gets really, really small, it does this notation. This is called scientific notation. And when it says e to the negative 5, it's saying you put 5 more zeros on the front of that. You move the decimal place over 5 places. If it said e to the 5, you'd move the decimal place this way, 5. But to the negative 5, you move it this way. So that's really, really, really small number. So you'd reject it either way in that case. But if, like, let's say this was 50 and 100, then that would change back to what it was before. See how that changed? Even though the proportion was the same, since the sample size was smaller, it made it so that we were basically less confident, but still we're still confident enough. All right, and if this goes all the way down to like 30, 20, or sorry, half, 15 out of 30, now all of a sudden, if could this be a sample of the real population? Yeah, we would have to accept the null hypothesis because these values aren't below what we thought they would be. Okay, they don't get to the cutoff. So if we reject that null hypothesis, we could be wrong, over 10% of the time. So that's what that sample size does to us. Okay? The more sample size we have, the more confident that we can be. 250. Okay. All right. So that's where we make a decision, and you just gotta. That's why sometimes it's helpful to draw this out, particularly in the early parts. You kind of like draw it on a paper and figure out what you need to do. Okay. You need to divide your alpha in half. So the p-value is the smallest alpha the observed sample would reject. So it's the cutoff. Another way to say that is it's the cutoff value. So if the null hypothesis is true, it's the probability of obtaining a result as extreme or more extreme than the actual sample. Usually based on, in this case, it's based on an ideal. All right, so here are the process. So the statistical software will usually help compute the p-value for you. So you compute that p-value. We just did it in Excel. Oops. We just did it in Excel right here. So this is the p-value. You compare the p-value to the predetermined alpha value, which in a lot of times is 0.5, or sometimes it's 0.25 if you divide that in half. But it could be anything. If we want to be even more confident, we would say the 99% level. But 0.95 is accepted. Lots of times that's what people do. Okay. So if the p-value is greater than the predetermined alpha value, then reject it, and the results are really significant. Sorry, if it's less than. If the p-value is greater than the alpha value, then do not reject it. And in our case, we did not reject because the alpha value, the predetermined alpha value, was greater than the p-value. We did not reject.
So on your Excel sheet, which one would be the p-value and which one's the alpha?
This is the p-value.
Okay.
This is the alpha value. Yeah, the alpha.
And that's the alpha divided by 2.
Yeah, and this is the alpha divided by 2. So this is the alpha value for a two-tailed test. This is the alpha value. Sorry, for a one-tailed test. You're right. For one-tailed test, this is the alpha value for a two-tailed test. Exactly.
And with the political signs, let's just say, would be a one-tailed because you would assume that if there's signs are posted, you wouldn't have less than that. Is that what you're assuming?
It depends on the question.
Oh.
Any question can be two-tailed or one-tailed.
Oh, okay.
So, but basically, if you decide to go with one-tailed, what you're saying is you're confident that it's not going the other direction. You're basically increasing the the times that you'll accept that you'll reject the null hypothesis. You're increasing that probability. And so what you're saying is I'm confident that it won't be on the other tail. So yeah, you're making your test more powerful, but but it should make sense that you're increasing the probability that you make that error that it is on the other side. So if you can say, hey, I'm confident it's never going to be on the other side, either because it wouldn't make sense in my situation or because you want to ignore it for whatever reason, what you're doing is saying that it's not going to be on the other side. It's not less than, it's going to be greater or equal to. All right, so this is what we actually just did, this difference of means / proportions test. And there isn't like a smooth way to do this in Excel, or any other statistical software, because it's like 3 calculations. You just do it, and there is a way to get a z-score. You just use the book to get the z-score. Once you get your z-score, you can figure out the p-value and then compare it.
Your z-score is 2.48.
You could have gotten this from the book though, which would be the old way to do it, but that value right there, you could have gotten that p-value from the book, but it would have taken a little bit. This value right here is the z-score, so you could go look in the z-table, and 2.04, the book, the number in the table is 4793. 4793. And remember that that's the area under half of the curve. And so it's really 0.4793. And so you say equals this, or sorry, 0.5 minus that. And you see how that number and this number, you know, they're within a little bit. We have more numbers here, so they're almost the same number. Okay. So that's the way you'd look it up from the book. This is the way that you do it here. This returns the normal distribution, and it returns the opposite, the area all the way up under the curve. And so you want the opposite of that. That's why I did 1 minus there and 0 minus over there. So I'll leave that on there. Okay. All right. So we can also do a one sample difference of mean test. We don't have to do proportions. We could do means. For all the tests that we'll do, there's this concept of degrees of freedom, and the degrees of freedom is often related to your sample size. And basically, it's the number of values in the final calculation of a statistic that are free to vary. You could think about each observation as a degree of freedom, because each observation that you have in your sample size is an opportunity for it to vary. Okay. So it's the minimal number of points which should be specified to determine all the data points. And that's actually why it's usually the number of samples minus 1. Because when a parameter has to be estimated, the calculation of a test statistic, the mean, let's say, a degree of freedom is lost. So you can't specify a mean with just one parameter. There has to be 2 parameters. I mean, there has to be 2 observations. So it's a number of observations necessary to specify that parameter. So the degrees of freedom is usually n minus 1, but we're going to see in some tests that that's different. Sometimes I'll try to explain why that occurs. But in some tables, it's important. But again, we're not going to be using the tables that often. But you'll see in the t distribution there is in the t distribution the degrees of freedom is simply n minus 1. But we're actually you could use the tables if you wanted to, but we're going to show you how to do it. just like in Excel and or with other software. Okay, so when we use inferential testing in GIS, we have a few questions. This is something your book points out, and we'll talk about this real quick before I go through some examples here. But we have some things to deal with. One is that the enumeration units themselves may or may not represent an actual population, or they could. And in some cases, like with census data, we actually have what some might consider a population. And so some people would say, well, if you already have the population values, then what are you comparing this to? And in those cases, you might not want to even use a hypothesis test, your inferential statistics. So when we have data, whatever it is, whether it's census data or a land cover map, and if that land cover map or if that census data covers our entire area, includes the entire set of the population, then sometimes there isn't a reason to do a hypothesis test. We just do descriptive statistics and say the amount of land cover in this area is this. However, if that land cover map represents if we know that that land cover map represents a sample, in other words, it's either not the entire area, or we know that it could be wrong sometimes, we could take a sample of the larger data set to make some inference about either the accuracy or some larger population area. So we can take a sample of a data set and do some inferential statistics with it. It all depends on the answers that we want to come up with. Like, is this map accurate? Well, it might not make sense to go to every single location to test the map accuracy. You might draw a sample and then compare it to some ideal or known value and make an inference. This is actually pretty similar to what we did with the yard signs. But let's just say we knew how some people voted. We actually had that data. Okay. But then we wanted to check and see if we just did a random sample of the population, if those values were different, then we could do that. And then finally, it is possible to just treat the population as if it's a sample. So if we have, like, let's say a data set that contains all of the observations in Mississippi, and we want to compare it to all the observations in Alabama, if we could make an argument that even though we have the population data, there's some element of randomness that could have created these two distributions in these two states. And we want to know if the underlying cause of the pattern that we're seeing could have caused these two populations to be different just because of randomness. We can still use inferential statistics to test that hypothesis. In other words, what we're testing in that case is the mean value that we see in Mississippi different than the mean value in Alabama. And so what we're trying to do is say they should be the same, and there's some underlying process. Our hypothesis is that our alternative hypothesis is there's some underlying process that's made the values in Mississippi be different than the values in Alabama. And we want to test that hypothesis. Even though we have the population values, we're testing it, and we're assuming that they're kind of like samples of some process that we don't understand, but we are trying to test whether or not these processes that created this value, this mean in the two states, is different. And if we could like rerun history, what's the probability that if there is some random process that they could have produced a different value in either of those states, just out of chance, or if there is a real underlying difference in the process that created that. I guess like one of the examples might be we have all of the car accidents. So we know the proportion of car accidents in Alabama, and we know the proportion of car accidents in Mississippi, or we know the average car accidents per driver in both of those states. Okay, so that's a proportion. And if we tested, are they significantly different from each other? We already know that they're different from each other. We see the numbers, and if our population is really Mississippi and Alabama, we don't really need to run a hypothesis test to say, are they different, right? But if we do run a hypothesis test, what we're actually testing are they really from the same population, or is there some underlying factor that's causing car accidents to be different in Mississippi versus Alabama, and is it just some random element that has made them different, or is there something that's actually causing that? So if it turned out that they had a small p-value like this, what we're saying is if there's no random element to this, there's something different about Alabama than there is about Mississippi. See what I'm saying? So that, like if we scaled these numbers up, so if these represented the total number of drivers in Mississippi here, let's just say 3,000. And actually, I'm getting a little bit ahead of myself. So if I compared it to some overall proportion, because it's not, right now we're not comparing two proportions, we're just comparing one to an ideal value. So here we say, okay, well, 200 people got in an accident. I don't even know if this is right. But in reality, it was, well, the ideal was 300 and 40,000. So we're getting a really, really, really small number. So the probability that those two are just by chance is not very big. But let's just say that they were really close. 212 and 219. So let's just say that the proportions were really close. Even though we have a really large sample size, we wanted to know if randomness could have made them different. Then now we've got a p-value that's really large. And so we would have to accept the null hypothesis and say, no, that difference could be explained by chance. In other words, crazy drivers are everywhere, and there just happened to be a few more accidents in Mississippi or Alabama that year. See what I'm saying? Okay. But if this was 500, all of a sudden it gets way off. So even a difference of, let's see if we can find the cutoff. 300. Yeah. No, this is really big, but that's now we're actually getting into the other side of the curve, so we have to not say 1 minus. 250, 240. Yeah, so here we're getting close. We're rejecting a two-tailed hypothesis already. So in other words, if you wanted to, you could kind of fiddle around with it to find out where that cutoff would be. Okay, so. Now these don't equal that anymore, but now we're fiddling around with it, and we're getting close to where that cutoff would be for at least for a two-tailed test. Okay, for a two-tailed test, this amount of differences, 212 to 240, is significantly different. So there's something different happening. See what I'm saying? So that's what that tells us. So there's all three of these possibilities. Why we would, in other words, this slide is why we would use inferential testing in GIS data. So one is we might just use descriptive statistics. Two is, well, in some cases we might be this comes in to play a lot when we're testing the accuracy of a map. But there are cases where we just have too much data. We want to check everything, and then finally, we are treating the population as if it's a sample because we're comparing the two samples to see if they. The two populations to see if they really could be similar or if it's random chance that has caused a difference. Okay. All right. So you always have to consider these. What's the population you're considering, and investigate the variables themselves. Look at your sample data, and then think about the inference that you're making about the population based on the sample of the data. That'll go into your hypothesis tests, and then your cutoff value is really a reliability measure for your inference. In other words, what you decide your confidence interval is you're saying, okay, how confident am I in my technique? How often will it fail? All right, now this actually is introduced here in chapter 9, but isn't tested. I mean, we don't talk about a test until chapter 10. There are what we refer to in the statistical world as parametric and non-parametric tests. Okay, so parametric tests are tests that have assumptions about the underlying distributions, particularly that parametric tests always require actual numbers, like actual real numbers that can be added. We would call that interval ratio scale data. So parametric tests always require interval ratio scale data. They often require that the underlying populations have distributions like being normal. That's usually an assumption. Okay. Now, what we're really assuming is that the sample means are normally distributed, which is a pretty safe assumption. So it works in a lot of the cases. Parametric tests can be used more widely than I think people think they can be used a lot of times, but there are cases where they're violated. Okay. Now, in some cases where where they are violated, we want a different type of test. So if we have values that represent ranks, like let's just say we have, instead of having, let's just say we did a survey and we said people are satisfied, unsatisfied, those things like teacher evaluations are like that, right? Where they have a scale on 1 to 5.
Agree, disagree.
Right, exactly. So if we wanted to test whether or not, my class got lower scores than another class, we could turn those into numbers, but strictly speaking, that's just because you turn ranks into numbers doesn't make it so you can use a parametric test, because the violation of what a mean is off, because some people in their mind might have a different definition of satisfied versus unsatisfied. But what we could do is turn those values into ranks and use a non-parametric test. So we'll talk about non-parametric tests in chapter 10, but they can accept they can't accept nominal data, but they can accept ordinal data. And so if it doesn't truly have it's not truly a number, but it still has an ordinal rank, you can use a non-parametric test. And also you can use it on any distribution. So if you're concerned that you're using a population that has a very abnormal distribution that's not normal, then you would use a parametric test. And the book introduces this concept, but we don't talk about it until chapter 10 here. So
on some of you mentioned like how satisfied are you questions and how you can't really derive a meaning from that. What if it's like one of those questions where it says, one being the least satisfied, two being the most satisfied, and give me a numerical value for satisfaction?
Right. Okay. So you can derive a mean from that, right? Because a mean, you could just take, if you have 1, 2, 3, 4, 5, you could add up and figure out what the mean value is, right? Mm-hmm. However, that mean value doesn't have the same power as a mean value that's calculated on real numbers, because that's what I was trying to say, because the difference between your 2 and 3 may be a lot different than the difference between somebody else's 2 and 3.
Okay.
In your mind, the way that it's really a rank. It's not an actual number. And so comparing two different people's means directly isn't as valid, because the underlying math no longer works in terms of, oh, everything should be 2 standard deviations away from the mean, because distance no longer means the same thing. Like the difference between a 1 and a 5 for one person may be totally different, and it doesn't really mean that you did 2 times worse or 3 times worse if the number is twice as high, right? Like,
Right.
And so these non-parametric tests are testing the same thing, but they do it in a different way so that it doesn't assume anything about distances. So in fact, the way that they calculate is they operate, most of the ones that we'll talk about in the next few weeks, they operate on, when I say distance, I don't mean Euclidean distance, I mean
Like on the number scale.
on the number scale. So if your income was 20,000 and somebody else's income was 10,000, you really earn twice as much as them, right? So there's a real number on there. But they use ranks instead of using distances, and then those ranks become the comparison of the rank values to infer which ones are higher and which ones are lower. And we'll talk about those like right now, but the slide is in chapter 9, but we don't actually start showing an example of this until chapter 10. All right. I want to be all done by 3 o'clock so that we can just cover the test for the rest of the time. So I'm going to switch over to chapter 10. We'll take a break at that point, and then we'll.
10 is not going to be on the test review.
10 is not on the test review, but the test review is in chapter 10. Okay. All right. So 10 is really not that. Like, you should be able to do the 10 homework really, really quickly once you understand what's going on in chapter 9. So once you understand how to come up with your hypothesis test, chapter 10 is just, in fact, chapter 11 is the same way. So chapter 9, 10, and 11, once you understand the hypothesis test and figuring out the tails, you're just running a different test in the statistical software. Okay. So here we're going to introduce several more tests in chapter 10. So we've got, so far, if I go back to chapter 9, so far we looked at these one sample tests, one sample z-test, one sample t-test, which are really the same thing, okay? And then the one sample proportion test. This is the only one we actually calculated out. Oh, but by the way, we could have done, oh, that one doesn't, okay, that's a 2 sample test. So for a 1 sample test, yeah, you just calculate it out by hand. But let's look at how easy that is. Okay, so for a 1 sample test, we have our so this is the proportions. Let's just say we have something really simple like I'll have my fall 2019 fall or sorry. Let's just say somebody says that the average grade in my class should be 72. Okay, should be 72. The mean score should be 72. And then in fall 2019, I got everybody 72. That seems low. 78. Okay. I'm just saying this is just made up, like what the university might say. Oh, you should give. They probably would never say that.
Should have a normal distribution.
Yeah. Right. If they said I had a normal distribution, but the average should be 78, then and the standard deviation should be like 10 maybe. But I found out that I actually had an 81, and the standard deviation was 12. And they said, well, it's not the same. Well, I could say, well, if this is just a typical set of a class, and I had, let's say, 15 students. So that's the number of students. So this is the standard deviation. This is the this is the means, and then this is the n. Okay. So what I want to do is to say, okay, my null hypothesis is that these two, not these two, that the distribution of grades that I saw could have really come from what should be the ideal distributions of grades. It could be just random chance that some people got higher grades than normal, right? And so that's the null hypothesis, is that this sample of people really does equal the ideal, that this is just a random set of values. So I'm comparing it to an ideal, to a known population value. Okay. That's what this one sample t-test does. So I'm doing one more in chapter 9 because I didn't quite get there. Okay. So x bar is the population, the sample mean, and mu is the population mean. And here with a t-test, we assume that we do not know the real standard deviation. That's what that means. With a t-test, we assume we don't know the standard deviation. With a z-test, we do need to know the standard deviation. Okay. The population, that's population standard deviation. So we'll do both. Okay. So with a t-test, we're going to say that is equal, the z-score is going to equal, do the t-test first right here, is going to equal the sample mean minus the population mean. That's this part. And then we're going to divide that by the sample standard deviation divided by the SQRT of the sample size. And this also needs to be divided by, see, so there's two divided by symbols there. So I messed up. Put a divided by symbol there. So it's this, and I need to put that in parentheses. So it's this divided by that. That formula is this value. Okay. Now this is the z-score, right? The t-score. This is the t-score. This one right here, the t-score. So I could take that value and look it up in the table, or I could do the t distribution returns the left-tailed student's t distribution. Yeah, so x is this value. The degrees of freedom is this value minus 1. That's the degrees of freedom for every test is a little bit different, but it's that minus 1, and then we say true. So now we're getting the cumulative probability distribution function. For some reason I'm getting some feedback there. Okay. Now those values are similar, but do they make sense? So what's this number right here? Yeah, it's the t-score in this case, but it's the test statistic. In this case it's t, and then we'll calculate z down here. Okay. And then this is the area under the curve. And since it's greater than, it's the area under the curve up to that point, and I actually want the other side. So 1 minus that will give me the right value. So there's the p-value. In other words, So am I going to accept or reject the null hypothesis? Probably I would want to say I would probably want to say that it's non-directional, okay? Because in other words, each year I'm going to get sometimes higher, sometimes lower, right? So I would say that the alpha, what should the alpha value be then if it's two-tailed? .95 divided by 2. I'm going to say equals there. Okay. So should I accept or reject that?
Where'd you get the 9.5 from? Or is that supposed to be just be 9.6?
No, that's the test statistic.
Oh, okay.
No, the alpha value is
How accurate we want to be.
yes.
Okay.
So we choose that. It's
Oh.
1 minus the alpha value, by the way. I messed up. Yep. That's 0.25. So should I accept or reject based on those numbers?
Except.
Yes. Why?
Because the p-value is bigger than alpha.
Right. The p-value is bigger than alpha, and the p-value represents the probability that just occurred by chance, that they're equal, that they really are. If they really were equal, then I would expect that almost 20% of the time I would get a value like this. So I accept the null hypothesis that they're different, right? Okay, now if we want to do z, the formula changes just a little bit. It's still the mean minus the ideal, but we would divide it by here. We divide it by the population standard deviation, which is this value, divided by. See how that's different. Divided by the SQRT of the sample. And I want to put a parenthesis around all of this so that it gets done first. So now we have a little bit different number. Okay, see how that used this one? This used that one. Okay. So first of all, we're using a different standard deviation. Even if those numbers, well, if those numbers were the same, we would get the same. We get the same test statistic, but we would include that test statistic would be different over here, because here we ask for the t distribution. Here we'd actually ask for the normal distribution. So we'd say normal, and we get the the x is this value, the mean is 0, the standard deviation is 1, cumulative true. One standard deviation over, oh yeah, and it's 1 minus, still 1 minus. Okay, so there, now our p-value, did it go up or down?
Down.
Okay, so using the z-table, what we're saying, when that p-value goes down, using the z-table, we're actually a little more, it would happen less often, because we know the sample standard, because we know the population value, we can be a little bit more confident that value isn't. But is it still enough to reject the null hypothesis? No. So either way, because the alpha is the same, even though that number's changed a bit, it's still not enough. So even though we know the population standard deviation, even if it was the same, actually, notice that it did go down, but not much. Okay. And as the sample size increased to 30, watch, these numbers will get well, they're still not too close, but eventually they'll get really close together. go to 100. Yeah. Actually, they're getting further away. Something up with my. Oh no, that's right. It's the opposite of what I was thinking. So as the sample size increases, we're more and more sure about our z value than we are our t value. Back to 12.
30, we would reject it, right? At
What's that?
30? Like when you make n 30, we would reject it because it goes higher.
Yeah. So, in other words, what's happening is that as n increases, we become more confident in our number, and so yes, we would reject, still not reject it, but 50 would still not reject either one of those, right? That's 60. We would reject 70. If we had 70 samples, we would reject both of these. In other words, if we had 70 samples, we could reasonably say that these two values are significantly different. If we have 70 samples, let's see if we do 65. If we have 65, still not 60. If 63 samples, we would reject it if we knew the population mean. But if we didn't know for sure what the population mean was, we'd still not reject it. Okay. Now, just because I played around with those numbers, if this was a real scenario, it doesn't mean anything. In reality, it's either true or it's not true. Your null and alternative hypothesis. We're just estimating how often this would happen, like how weird this event was, and so we're using that level of offness, that level of weirdness, to make a decision and decide whether or not we're correct or not correct in the assumption that we're making. In reality, it's either true or it's not true. Like we're just estimating a value that's going to help us. So this is one sample proportion, one sample difference in means, both z and t. Yeah.
So your null, can you give me the English version of what your null hypothesis would be for this one?
For this one, it's that. So my null hypothesis is that the grade distribution, the mean grade this semester is just the same as is a representative sample from the population ideal. So it's not different. So the grade distribution this semester is not significantly different than the ideal mean score.
Okay.
The means of the grades this semester are not significantly different than the mean score. They're equal to each other. So I actually said the null hypothesis, right? So the mean grades this semester are equal to the overall mean score.
Or close enough to.
Yeah.
Okay.
Yeah, they're.
So this is saying that this class is, well, when you go back to the lower in this class, isn't like the normal. It's outside of the realm of normal when the p-value's bigger.
Yeah, so we're saying when the p-value, now it's outside the realm of normal.
Okay.
Because we have more samples, we're more confident that this really is outside the realm of normal. It's significantly different. So yeah, back when this was 15, and we were rejecting, we're saying, yeah. So if we only had a sample of 15 students, we would expect to see a value this weird.
So this is saying that this one class isn't that far out of the normal.
Right.
Okay. Cool.
Yep. Exactly. All right. Okay. So we covered now. I've actually shown each of these. Now for everything beyond this, that was this one, this one, and this one, and this one. For everything beyond this, it's really, oftentimes you don't even have to calculate the test statistic. So depending on the software that you use, you could go into the book, and the book shows you how to do it. But in practice, we're just going to get this p-value and compare it to alpha. Okay. And by the way, we did two-tailed here, so we were saying, is it different? If we just wanted to say, oh, is this higher than normal? Then we would compare this to 0.5. And so we could have rejected it earlier. All right. Okay. Going back to this one. All right. So now we're moving on from one sampled to two sampled tests. So in order to distinguish between the two, with the one sampled test, you're comparing it to some ideal or to some population value. With the two sample tests, you take two samples of a population and you're comparing to see whether they're the same or not. Okay. Now your samples, you may divide your samples up. You may decide, oh, is the average number of hurricanes, the average number of hurricanes in Florida significantly different than the average number of hurricanes in Louisiana. Okay. Well, it probably is going to be. I mean, it's a lot more coastline, but if you wanted to test that, that's a two-sample test, Florida and Louisiana. And really, my example before with the proportions one was really a two-sampled example comparing Mississippi and Alabama. That's why I kind of I kind of said it wrong. I tried to backtrack, but it didn't really work out. But
using the last example, it'd be like, oh, your fall and your spring semester classes, you were comparing their grades.
Yeah,
okay.
Exactly. Fall and spring. And then the null hypothesis is that the average grade was equal. Or I could do, in fact, I've calculated this number out, but I've never run a significance test. I always try to make sure that the coast. I'm always curious as to whether or not the coast or the Hattiesburg campus grades are different. So I'm curious about that. So
do it for our midterm.
Yeah. So anyway, I'm curious about that. I was calculating, but I could find out if they were significantly different. With such a small sample size, it very rarely proved to be significantly different, right? That's what we see, even in this scenario. Like, let's say, if we go back here, when we only had 4, we're getting pretty far out in terms of that ability. But okay, so so the two sample different tests. So they're going to test between two samples in different ways. There are 4 or 5 tests that we're going to go over. So the first one here is called a two-sampled difference of means test. Okay. So in each of these cases, we are going to cover the parametric test, and we're going to cover the non-parametric version of that test. Okay. So the parametric tests, you can actually run a test. I'm not going to do it today, but I don't think we have time. And sometimes it's pretty easy to see, but you can actually run a test to see how normally distributed a distribution is. We'll probably do this later in the course, but right now we're not going to run that. So they assume that normally distributed data, technically that the mean is, the distribution of sample means can be normally distributed, which is a pretty safe assumption. And they also require numerical data. And so here you need to do a Z or a T difference of mean test. And here it truly gets to the point where you can you're safe to usually use the T test. And then as you get higher, it converges on the Z. Okay. Then the non-parametric test is called the Wilcox rank sum W test, sometimes called the Mann-Whitney U test. Okay. All right. So So the test statistic is formed by z, and you can see that the basic, we're not going to do the math anymore here. You can see that the main difference is looking at the top, the numerator is the difference in the means. And the denominator is a standard error that's related to the standard deviations that are in both of the samples. So it's still trying to normalize or scale down that distribution to match the normal distribution. But we're just looking at the difference in the sample means and the difference in the distributions. Okay, so that's how it's done. You could see that the math is related, is that we're just dividing the difference in the means by a difference in the standard deviation values to create the standard error. Okay. Now, how we calculate that standard error, there's two different formulas for it. And again, we're not going to calculate these out, but you should know this, that when we're taking two sample differences, if we can assume that those two samples come from the same population and should have the same standard deviation, we do what's called the pooled variance estimate. And if we don't assume that they come from the same population, we would do the unpooled estimate. These are actually all the pooled estimates. All right, so here it is. Here's a simple table from your book that shows why you would use it, what you assume, and then the hypothesis that you can derive from it. Okay. All right, so let's do this in Excel first. I'm going to create a new sheet here, and I'm just going to create some numbers. 1, 2, 3, 1, 2, 1, 2, 3. This represents a sample. These could be the number of hurricanes that happened in a given year in one state. This could be 2, 3, 4, 1, 2, 5, 6, 7. Let's say I have more data. Let's not go that high. Let's say I have more data of this other state. So I have more data here than I do from here. That's not a problem. So I want to ask, is the average number of tornadoes different in this state versus in this state? Not tornadoes, or hurricanes. Does it look like they'll be? Maybe we'll add another 4 here to make it a little bit different. Does it look like they're different? Well, I don't know. Is it significantly different? Let's find out. So we need to run the test. The test will return the p-value. So all we do is say t-test. And it requires 2 arrays. So we're going to choose this array. We're going to say comma, this array. And it goes through, it calculates the mean, it calculates the standard deviation, it does all that. We do have the option in Excel to specify whether it's a one-tailed distribution or a two-tailed distribution. And you'll see all it does is take that p-value and doubles it for you. Okay? So for now, let's just do one-tailed, and I'll show you how it changes. And then finally, we have the type. We're not talking about paired yet. We're talking about these two so far. So here we can specify whether we assume that our variances are equal or we assume that they're unequal. If we assume that they're equal, then basically what's going to happen is that it's going to pool the variances together, and that variance value will be smaller, and that'll affect the standard error. The standard error will be smaller, and so we are more likely to get a smaller p-value. What happens there? So only choose this one if you are really confident that they should have the same variance values. Now, I'm going to say, well, with hurricanes, they really should have a similar variance associated with them. So I'm going to choose it this time. We maybe make an error, an argument either way. Okay. All right, so we've got all of our information, and as soon as I hit return, that's my p-value. I've got my p-value. I didn't need to calculate anything to get it. I've got it. That's the p-value. How would the p-value be different? Well, let me just let's see. We could see how it would be different. Whoops. If I didn't do pooled variance, if I just did unpooled variance, and you could see that my p-value is slightly smaller value. And what does the p-value represent?
Probability that it happens by chance.
Yeah, well, it's the probability that by chance I would get this if the null hypothesis were true. Okay, so would I accept or reject the null hypothesis here? Are these two values significantly different? And that's the null hypothesis, right? The null hypothesis is the average number of hurricanes in this state different than the average number of hurricanes in this state?
Would you need an alpha to compare the two?
Yeah, I need an alpha. What alpha would I want to choose? I choose the alpha though.
Yeah. So we can keep with the 0.05.
Yeah, 0.05. Or sorry, 0.05. So would I accept or reject that?
You would accept it. Okay.
I would accept the null hypothesis that they are equal. Exactly. Okay.
So even though one has 2 more entries, it can still be equal
Yes.
as far as your average.
Your samples do not have to be of the same size. So I could come in here and play with these values. What if all of a sudden I had 10 hurricanes this year? Okay, well, those are still not significant, right? 15. And now all of a sudden, well, it's still not significant. My sample size is really small though, right? Like let's say I have 100 years of data, it would probably change. That changes it. So those are significantly different.
So that might be like South Carolina versus Florida.
Yeah. I'd say even if this was 5 and 3, yep, those are still significant. Those two, even though those are small values. Okay. All right. So if I were to pull up the homework, because you have homework here, chapter 10. I'm just going to do one real quick, and I won't save it here, so you have to reproduce it. But what if I want to ask the question here? What if these are a sample of new home values, and I want to find out if the new home values are significantly different in 2005 versus 2010? It really is as simple as saying, well, first of all, let's find out what our null hypothesis is. What's our null hypothesis here in the scenario I just came up with?
That the house, they stay the same?
Yes, the house price stays the same. That's the null hypothesis. Now, the alternative hypothesis could change. If it's one-tailed, which is actually, this one from the book is actually one-tailed, because they're saying, did the average prices of homes go down? Because in 2008 we had a big a decrease in home values. So they're asking, is it basically, has it recovered or is it still lower? So when we answer this question in the class, it's a one-tailed. Okay. And if you were curious, you could calculate the average. That's why it's always nice to know how to calculate descriptive statistics, even if you know the formula for the. So here's 2010. The book doesn't ask for this information, but descriptive statistics are often useful for exploring. There's 2005. So we do know it went down, right? But could it just be, could they really be the same population? That's the question we're asking. Are they statistically still the same? Because even if this represents all of the houses, it's not a true value of all the houses on the market, right? Like these are just the sold ones. So we want to ask, are these statistically similar, the same? the null hypothesis is, are they equal, or is this significantly lower? That's one-tailed. So it's simple as going like this, equals t test. We get our array 2005 and our array 2010. And then we need to say whether or not it is one-tailed. We only want one-tailed. So what that'll do, if we say one-tailed here, is that it will half the p-value so that we don't have to double the alpha value.
You said that's because they only want to know if it went down. If they just wanted to know
Yes.
if it changed at all, it'd be 2-tailed.
Yep. And then here we would say that, you know, this is really kind of like, you know, it's a judgment call. And if you could justify that the variances should be the same, in this case, I think it's even a bigger justification than the hurricane one. But there's one thing you could do is calculate the variance of each and see if they're kind of similar. All right, so that's the p-value. So do we reject, or it's actually almost the same as the hurricane one, but
Or we would accept it
right,
if we do 0.05.
right. Even if we did like 0.95. So what are we saying when we accept it?
That they are not significantly different
Right.
in years.
That they're not significantly different in years. So
pretty much that county bounced back from 2008.
Right.
Essentially.
Yeah, that it's either bounced back or it's on its way back. There's no significant difference. That the difference could just be chance. In other words, that home sold that was worth less than the home any given year. Yeah.
So I'm sorry, but maybe I guess I just lost this. What does the 0.315, like what is that? I mean, you're saying that you would, what does that even, does that mean it's 32% low? What does that mean?
It's the area under that probability curve. And so what it's saying is, right, because, okay, how many records are there here? 41, 40? So this is 40 houses that sold in 2005, okay? And this is 40 houses that sold in 2010, but they're different houses. Like, you know, this house could have been some, you know, really crappy house, and this house could have been some really nice house. And because we're dealing with data, the randomness of the data, that we just got 40 samples in this time and 40 samples in this time period, we can't just say, oh, well, because this went down, it's for sure lower. It could have just been chance that a really crappy house sold then and a really nice house nice houses sold then. And so this p-value is saying, is there some, the p-value is saying the probability that the two samples are drawn from the same overall population. That's what that's saying. That's the probability that they're drawn from the same overall population. So the way we can interpret that is to say that if these two samples are, if we can assume those two samples are equal, we would expect to see this type of difference 31% of the time in a sample of 40 homes. Still not? Sorry.
What I'm trying to see is like, just looking at that number, that p-value, why does that, like, when you look at that number, how do you know whether or not it's to accept it or reject it?
Okay.
Just by looking at that number.
Okay, so the p-value is the area under this curve. So when it's 0.31, like we're somewhere over here, because the area under half of it is 50. And so the p-value represents the probability that in other words, the number of times that you could get that value or less given these two samples, a sample of size of 40.
Okay.
So the p-value, another way to say the p-value is the probability that, well, the probability that given that it's, well, a shortcut to it is the probability that those two data sets come from the same population. And that's not strictly true. It's actually the number of times that, because the probability that these two came from the same population is either 1 or 0, right? But we don't know whether they came from the same population, right? But it's the probability that if we designed this experiment and we collected 40 samples from each, it's the number of times that we would get a value like this out of 100, and it would be 32 out of 100 times that we get that. So in that way, in terms of the user, like in terms of us, it is we can think of it as the probability that they are from the same population. Because we're using it. But in reality, it is either from the same population or it's not. Like it's something that's actually occurred. But we don't know whether it really is. And so we're trying to say, yes, they are from the same population, or no, they're not from the same population. That's what the null and alternative hypothesis is. And so we're saying, based on our data, they are from the same population. And we're using that number because we say, well, about 32% of the time, we would be able to see this thing happen with our data. And so we're going to go ahead with the assumption that they are from the same population. And that's another reason you say 32% chance. Well, that's a lot less than 50 or 70, but that's why your null hypothesis needs to be the one that you're more comfortable with. Because you're saying, in other words, it's the one that it would be the bigger mistake to get rid of that null hypothesis. It's a bigger mistake, in other words, to say that the alternative hypothesis is true when it's not true.
But the county hasn't bounced back.
Yeah, that county hasn't bounced back.
So there's like a 68% chance that you would be wrong if you said that this county hasn't bounced back from this crash.
Yeah. So that's that value. So the simple short answer is that's the probability that these two are from the same population, but really it's the probability that we're going to make an error if we choose to say that they aren't from the same population. And that's a pretty big probability that we're making an error, right? 31% of the time we'd be making an error if we chose to say these aren't from the same population. Or
So we accepted this one?
Yeah. So anytime the p-value is relatively large, remember p-values range from 0 to 1. So anytime the p-value is large, in other words, bigger than our cutoff value, we accept the null hypothesis. Exactly. Okay. So what are some of the other ones here? So here's the water use. Water use, exact same thing. We could even, oops, I'll just retype it. So t-test, you can see how the homework's going to be pretty easy. We do need to take a break here real soon. Okay, t.test, and then you're going to choose your two arrays. Oops. And then this one, I forgot whether in the book this is one or two-tailed. So let's go with two-tailed. And then the type is going to be, let's say that they're unequal variance this time too, because what we're doing here is saying that the people that have pools use more water than the people who don't have pools. I guess that would probably be actually a one-tailed test. Because you're saying more water. If you say that they use a different amount of water, then it would be two-tailed. If it's that they use more or less water, or use that's one direction. Yep. So yeah, if we're saying that they use more, then it's a one-tailed. But here, one thing. Watch this. So I do want to show that these values here, if I say two-tailed, equals this divided by that. Whoops. 0.5. So this is exactly half that all the time. So Excel doesn't actually need to put that in there. It's just for fun. Like, I mean, it just makes it easier for you. But if you want to always do two-tailed and divide it in half later, then that's fine. But just remember that it does that. Python, I will show some examples of Python. I may hold off until after spring break. But Python does not. On some of the tests it actually does, and some it doesn't. Most of them it doesn't. It only gives you the two-tailed. So you'll have to. Okay, so that's that. So anyway, would we reject or accept the null hypothesis there? This is the one-tailed, and this is the two-tailed. Does it really matter? We want the one-tailed, but in this case, does it matter? Remember the cutoff. I don't know what the book says to use, but let's just use 0.05 for now. And what was our null hypothesis? Yes, the null hypothesis is people with pools use the same amount of water as people without pools. And the alternative hypothesis in this case was that the people without pools use more water than the people with pools. Or sorry, the other way around. That wouldn't make any sense. People with pools use more water than people without pools. And notice that Excel and on all the statistical software doesn't care what order you give it in. It doesn't even care if you specify one as the more of the other. You specify the hypothesis, and it doesn't actually even matter to it what the test is. Okay? So anyway, that is the p-value, and this is the alpha value that we've chosen. Okay. So should we accept or reject it this time? Yeah, we reject because this p-value is relatively small compared to the alpha value. Smaller the p-value is, the more opportunity you have to reject the null hypothesis. And when we reject the null hypothesis, we're saying that these two are not equal. And so we reject it. The alternative hypothesis is that the people with pools do in fact use more water than the people without pools. Okay.
So earlier when you used in the example before, it says they belong to the same population.
Yeah.
In this case, they belong to two different populations.
Right. So people with what's that?
Go ahead.
People with pools are different in terms of their water use than people without pools. Yeah. Now, that's in terms of their water usage. They're a different population in terms of their water usage. Now, it doesn't say anything about their politics or anything else. Like it's possible to have different populations in the world. Like, yeah. So.
But in terms of the water usage.
Yes. Yeah, like if I had these divided out by Trump voters and non-Trump voters and had their water usage, and I found out the same thing, that they were significantly different, then the two populations, then what I'm saying is that there is a difference between water usage for Trump voters and non-Trump voters. But here we did, fairly obviously. Okay. All right, I'm gonna probably, let's see where I am. Okay, yeah, I'll just end right here. I'll just talk about this Wilcoxian rank sum, and then we'll end. And I think, yeah, I'll talk about it real quick, but I'll re-talk about it next week. So in the rank sum, it's really taking the difference in the ranks. So we take all the data, we add it all up. We take all the data and we put it in a rank. So if we were to do this with this data, with this Excel data, we'd take all these values and we'd stack them all up and rank them. And so we'd mix together the water use people and the non-water use people. And we would line them up from highest to lowest, and we'd rank them all. So the very highest water user would be ranked 1. The second highest water user would be ranked 2. The third highest water user would be ranked 3, and so on. Then we pull them back out into their groups. We'd have a water user, a pool, and a non-pool, and they'd have ranks. The number 1 water user might be in one group. The number 2 water user might be in another group. And so if we take their basically their average rank and we compare their average rank, it makes sense that if they are similar in terms of their water use, their average ranks should be similar. In other words, 1 might be over here, and 2's over here, and 3's over here, and 4's over here, 5's here, 6's here, 7's here. And so that those would represent that they were equally in there. But if 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 were all in the highest water users were all in the pool group, and the bottom were all in the other pool group, the average rank value for the non-pool users would be much higher. So that's how that works, and it works better on data that is ranks. It's 1s, 2s, 3s, 4s, 5s, because we no longer have to assume that the data is normal or even that it's a real number, because we're just talking about ranks. So the reason why I did want to introduce this is so that you see that for this, there's no way to do this in Excel except for calculate all the ranks out by hand. That would take forever. So a lot of data wrangling. But what I'll show here, and then we will take a short break and then do the test review because some people have to go. So actually, maybe we won't take a break. Okay, so I have a little set of Python workbooks, and I'm not going to talk about all of these so far, but this is the one that I just talked about, the Wilcoxian rank sum test. And you can see now, this is like literally 5 lines of code, and 2 of the lines of code are just making sure that you have access to the right libraries. Okay, so here's the numbers, the raw numbers, and it takes care of ranking them and everything. So these might represent the number of hurricanes in a given year, and then these These might represent the number of hurricanes in a given year somewhere else. And I don't know, they wouldn't be decimal places, so we're going to think of something else. But these are two different distributions of data, and we run them, and we get a p-value, and we get a test statistic. We're just going to ignore the test statistic most of the time. P-value is what we care about. What's the p-value here? 0.72. So should we accept or reject the null hypothesis? Yeah, we accept the null hypothesis, which are, again, that these two come from the same, they're equal. They come from the same set of data. Oh, these could be the average teacher scores of geographers and geologists, right? They could be, because that would be an example of when we want to do a non-parametric test. So in other words, all the geologists, these are the average scores of 3 different geographers and 4 different geologists. That's our kind of program. And we wanted to ask the question, are the average scores that they get significantly different? That's the alternative hypothesis. So are they equal is the null hypothesis. So we run it.
Yes, they are close enough.
Yeah, they're close enough. It would be a mistake to assume that they're not, especially with that few observations. Now, obviously, as we get more observations, that p-value is going to go down because it does matter how many observations that you get. Okay. Now, this is one of the only ones in Python that does ask for a two-sided. So this is, are they different? And if we said one-sided and we ran this again, we have to say less than or greater than. So in this case, you actually have to specify less or greater. So you could see that number is basically half. 30. If the other one was 72, that's 36. That's half of that number. Okay. So there we're asking, is B less than A? So we'd still reject it, but we have that two-sided as the default. Okay. All right, let's stop there. But I'm gonna put Python a little bit back into these next few because there really isn't an easier way to do it. But you could see that we're not doing a bunch of data wrangling where we're taking a column here and a column there and adding and subtracting, and we're just taking 2 columns of data and adding them together. The only example where I put a reading in Excel in is one sample match pair. No, this one right here. So here I did a fake example, but then I also read in the water usage data and calculated the p-value, and it is the same as the two-sided p-value there. If I wanted, there's no way to do a two-sided in this test in Excel, and in Python. Most of them aren't two-sided in Python. So if I wanted to get the two-sided p-value, I have 2 choices. I could either half that value, the p-value, or I could or I could half my alpha value. I could half one or the other, but I need to compare apples to apples. So I need to half one or half the other. All right. Okay, and then these examples are all on GitHub, but we'll do that. So we'll do that when we come back. So I do think that it was important to cover a little bit of that because it kind of gives you a flavor of that. And let's talk about the test review here real quick. And what's going to be on the test. And then we'll get out. Sorry we didn't take a break, but I want people to be around and not have to leave. Okay. So I'll make chapter 10. It's not going to be due. It's not going to be on the test. It's not going to be due till a week after we get back from spring break. Okay. All right. So the test. This test is going to be open book and open notes. Okay. You still need to study though, because you'll need to understand the concepts in order to find information that you need to answer the questions on the exam. There are going to be some calculations, which I'll talk about. Okay, but they should be pretty simple. Okay, so in chapter 1, we need to make the distinction between descriptive statistics and inferential statistics. These are both defined in chapter 1 in the reading, but descriptive statistics are basically now we know a whole lot more about these. Inferential statistics are those statistics that are used to make a decision about a sample. Descriptive statistics are just statistics that describe data, that tell us, whether it's got a big spread or a small spread, or whether it's got where the mean is. These kind of gets into, if you know that pretty well, these are this chapter right here is what we're going to talk about some examples of descriptive statistics. Okay, so you do have to understand this concept of a population and sample, and these build off of each other. This is just where we introduce these concepts. So sample and a population. Be able to recognize the following types of charts. So in other words, if I show you a pie chart, a scatter plot, or a bar chart, you should be able to read the information off of any of these three charts. I know we didn't hit that very hard. I did assume that you didn't understand, or maybe that a scatter plot was a new thing. So we did talk a lot about scatter plots, or more than the other two. But you should be able to read any of them. Okay. And then, all right. Then the next one is you should be able to understand data. So what is data? What's a data set? And what is a data value? Data value is basically the intersection of a row and a column. And rows represent entities, features, objects. Columns represent their attributes. So we're talking about rows and columns of data here when I say data. All right, chapter.
The rows were like the occurrence, or like the.
Yeah. All right, chapter 2. So here I want you to be able to define this term aggregation. Okay, when I say aggregate, what do I mean? Well, that means that you take some descriptive statistic about some data, and you present that as a surrogate for that data. You've aggregated that data. Take the sum, the mean, the range, the standard deviation. You use a descriptive statistic. Aggregation is using a descriptive statistic to describe some data rather than just the data itself. And one of the pitfalls with aggregation is that if all you have is the aggregated values, there's no way to get back to your original data. That's something that you need to know. Okay. And then the ecological fallacy builds on this concept of aggregation, because the ecological fallacy is that some aggregation value, some descriptive statistic, applies to every observation in the original data set, or to any observation in the original data set. So the aggregated value is a summary of the data. It's not the individual records in that data. That's the ecological fallacy, is saying, oh, well, the average income is that in that area is 10,000. And so if you live in that area, you must be really poor. Well, that's not correct. We can use inferential statistics to figure out the probability of grabbing mostly poor people from that population, but that's particularly when we point out one single observation. We can't really do that from summary data. Okay. All right. We need to be able to define these two terms, discrete and continuous data. So these right here are basically ways to describe data. Okay. If it's numerical data, discrete data means that it occurs in even numbers. So the count of hurricanes in a given year or tornadoes in a cell or whatnot. Continuous means that there's a number that could be any number along the number line. The weight of an object, any object, could be a continuous variable. Now, it is possible for us to round it and turn it into a discrete variable, but we should still think of it as continuous. Okay. Now, we can also think of data as being qualitative or quantitative. So a particular data value, if it's quantitative, that just means it's numeric. If it's qualitative, that means that it is non-numeric. Okay, so that's the difference there. Now, sometimes we have to be careful because qualitative data has been assigned a number, like land cover. And that's still qualitative data, even though, in a raster, it's particularly in GIS data, urban might be coded 3. That doesn't mean that 3 has any number. It's just the code. It's still qualitative data. Also, a qualitative data might be a description. And in those cases, when we're talking about descriptions, then we're not really usually using statistics unless we're going to calculate up categories. And that's called classification. So I'm going to skip down to this one right here. So the book talks a little bit about classification methods. Remember where we did natural breaks, equal interval based on range, equal interval not based on range. You should basically know how the ones in the book are defined. You're not going to have to actually calculate out those, but you're gonna need to know the basics of the different classification methods.
Will we have to look at something and be able to tell what it is?
That might be a little bit hard.
Okay.
So no, it's more the definition. All right, nominal terms. Because it's pretty hard to tell just by looking. Now you could definitely say, well, A and B, which one's more likely to be this particular classification scheme? But I don't have any question like that right now on the test. So, okay, let's go back up. Levels of measurement. Basic classification methods. So when we do a classification, if we put them in classes, effectively what we're either seeing with our eyes or maybe what we're doing by labeling them is that we're putting them in different categories, which are nominal values. In other words, high, medium, low, or whatever categories we put them in. We're putting them in categories. It's important when we create categories that we make them exhaustive and mutually exclusive if we want to use statistics on them. Okay. All right, the term accuracy and precision, what you should know here is that accuracy has to do with how often a value, or how precise, not precise, I shouldn't use precise when define accuracy, how different a value is from a real value, from the truth. Precision is how repeatable a particular operation is. Or in terms of measurement, it's basically, numerically, it's how many decimal places it can be measured out to reliably. Okay. Levels of measurement here: nominal, ordinal, interval, ratio. It's important that you understand the difference there. I'll leave you to look those up in the book. I've talked about it several times already today. I want to get through this. All right, so chapter 3. Now here is where you're going to have to do some calculations, and it's open book. Not only is it open book, it's open notes, and you can use your computer. So you need to be able to calculate the mean of a set of data. Now I'm going to make the data set so small, like 3 or 4 observations, that calculating the mean will be easy. Calculating the median, I'll make it so that there's an odd number so that you can calculate the median. What's the median?
Middle.
The middle value. The mode is the most often repeated value. So if you know the definitions of those, and there's relatively speaking, you should be able to do the median and the mode without even doing any real calculations. The mean, you could either do it all by hand in Excel, or Excel has a method for calculating the mean. Okay, so those will all be easy. These should be just as easy. The range, the variance, the standard deviation, those are all in Excel as well. Well, actually, I don't think variance is, but remember, variance is a standard deviation squared. The range is the high minus the low. But I want you guys to understand these concepts. So you need to understand those concepts. They're not hard concepts to calculate. Now, you do need to know that skew and kurtosis are measures of shape and relative position, but you do not need to calculate those. So in those cases, I will give you two different distributions, and you'll need to know which one is more skewed versus which one is less skewed, or skewed in which direction, something like that. So no calculations for that, and I've noted that. Okay. Calculations here, but you can use whatever tools are at your hand. You don't actually have to calculate it, but you will have to interpret. Like, what does standard deviation? It's a measure of range. So you'll have to, if I ask you, based on the standard deviation, which one has a bigger spread, or if I ask you what unit standard deviations are in, you should look that up. Okay. Okay, aggregation issues in descriptive statistics. Now here's probably the most, well, okay, we're getting into things that might be a little bit harder to calculate, but still I'm only going to include 3 or 4 observations, but I do want you to be able to calculate a weighted mean. So go back and look at how you calculate that. But it's basically you multiply each observation by the weight, and you get a value, a weighted value, and you calculate the average of those values by dividing not the total, but the total divided by the weight, the total of the weights. So go look that up. I mean, in Excel it's this easy. So, you know, if this is what's on the test, this is very similar to what will be on the test. You get 3, 2, 4, 5, and your weights are 1, 3, and 4. So these are your observations. These are your weights. And then all you do is say this times this. You add each of those up. The sum of the weights is the denominator. The sum of the weighted values is the numerator. And so you say equals this divided by that. That is your weighted average. So the average value is 3.875 based on these weights and those observations. So something like this is what you'll produce on the test. Okay. All right, so that's the weighted mean. I'm not going to have you calculate the weighted standard deviation. Okay. But it's just one more step. You're just squaring the weights, and if you look at the formula, it's not that much more difficult. But that's some of the stuff I try to do in Python early. So I think some people probably wouldn't be able to. Anyway, I'm not going to do standard deviation, weighted standard, but I want you to calculate a weighted mean. It's an important skill to understand how that goes into it. Something that researchers would do a lot. What's that?
We're not doing what about the modifier?
Okay, so the modifiable area unit problem, basically it's related to, both of these are related to aggregation errors. So there's nothing to calculate here.
Okay.
That's not a calculation. That is that you need to know what that is. And basically what this means is that if we aggregate data, it's a separate problem that comes in through aggregation. So we covered the other ecological fallacy up there. But the modifiable area unit problem means that how we aggregate our data can determine the answers that we get for things like weighted means and and things, because if we chop up our data differently, we could get a different value for what the mean value is. It's the question of the Electoral College is a great example of the modifiable area unit problem. If the states were in different places, they had different boundaries, we make it a different answer for an election. And I'm not talking about whether or not it would be right or not. I'm just claiming that you could get a different answer, which I think is a true claim. Okay, so coefficient of variation. The coefficient of variation, the formula is in the book. It is the standard deviation divided by the mean, and you will have to calculate that. There's no formula in Excel that says coefficient of variation, but it's just the standard deviation divided by the mean. So you should be able to produce that if you're given either the standard deviation, the mean, or you're given a set of data. Okay, and what does it do? What does it tell you? It basically normalizes the standard deviation. It takes out the units. It makes it unitless. That's what it does. So you can compare standard deviations from different data sets and find out which one varies more than the other. All right. No problem. Chapter 4. Here, you're going to have to do a spatial measure of central tendency. You are going to have to calculate mean center. And it basically is the same formula for here, except for you're going to have two different, you're going to have X's and Y's instead of just observations. Okay? Again, I'm not going to have you calculate the standard distance. You only have to define it, or the weighted standard distance. So just mean center. No standard deviation. This would be the hard one. So you're also going to have to not calculate, but define the central feature and the median center. You have to know the definitions of each of those. And then the relative distance is a measure of dispersion, and it is the standard distance divided by the area of the smallest encompassing polygon, and that can be defined in different ways. Okay, but you're not going to have to calculate that either. Just define it. I just defined it for you there. Okay, and be able to know what it means so that you could interpret two different relative distance values. Okay, chapter 5. Here we talked about what a probabilistic process was. We have random and stochastic, these terms. They mean very similar things. Basically, if we have, this is what I was getting at today, actually, when I talked about processes. The underlying process that causes accidents in Mississippi versus accidents in Alabama, is that different? Because it's a process, it produces an actual distribution in real life, and there's an element of chance to it. Random means that it's totally random, and we'd expect it to always be the same. But stochastic means that there's still probabilities associated with it. We just either don't know what they are, or we do know what they are, but they're not exactly random. In other words, there's not an equal chance of every event happening. Okay, so that's the difference between random and stochastic. So oftentimes we could boil down a question as to whether or not what we're trying to find out if it's random or if it's a stochastic process, and is it a different stochastic process sometimes.
Pretty much if it's stochastic, it means there's another factor influencing it. It's not just random.
Yes, there's a factor influencing it, but it still actually it still manifests itself different every time. It's a process that has so many variables we don't understand the entire process. So why doesn't every tree grow to be the same height? I mean, they all grow nearly the same height, right? But we don't, we know that some of it has to do with the soil, some of it has to do with the sunlight, some of it has to do with this, but we don't understand exactly the process that creates a tree of a certain height, input and get a tree of a certain height. So it's a stochastic process. There's still some level of uncertainty, but we understand some of the variables that go into it that affect it. And so we can design experiments around that and use statistics to find out if this stochastic process is similar to this stochastic process, or if we change something, we could say this little thing was different in this experiment, and if the experiments didn't produce different results, then we could say that they're similar or that they're the same, even if they did produce some differences. Okay. What was just created by chance and what is actually a process? Okay. Now, if we always get the same result, it's called a deterministic process. And there's really no reason to use statistics on there. Right? Like if we always get the same result, it's a deterministic process. And its result should always be the same. So if there's any difference, then of course there was some difference in the process. Okay. But how tall trees grow is not one of those things. It's not deterministic. There's lots of things that aren't deterministic in this world. They're stochastic. Okay. So we don't often understand everything. And so one way that we can determine what the probabilities are associated with certain random or stochastic processes happening in the real world is by observing their relative frequency. And so relative frequency is one surrogate for probability. So probabilities can be derived based on relative frequencies. Now I do want you to be able to do some basic probability problems, but none of them will be as complex as the homework. So we're talking about saying, for basically you're looking for the intersection of two rows and columns in counts. So you should be able to say, okay, well this is the probability of, for a particular event, this is the probability of all events happening. That goes on the numerator, or not the probability, the count of all events, and then the denominator is the probability of that specific event happening, or the count of that specific event happening. So the count of that divided by the count of all events.
The total's on the bottom.
Yeah, the total's on the bottom. Okay. And you should understand if they're independent of each other, then we can multiply their probabilities, and if they're when we would want to add them. Okay, but you don't have to do any of the dividing by the one. This one's dependent on that one, and that sort of thing. That's not on there. Okay. Okay. So discrete probability distribution. Here's where we're going to get into binomial, geometric, and Poisson distribution. So we're not going to actually calculate any of this on the test, but I will have pre-filled out tables, and you'll need to recognize which table applies to your situation, and you'll need to answer questions by looking up the values on the table. So if I tell you this table represents the binomial distribution of this particular scenario, or more likely this scenario happens, this is the binomial values from that table, tell me the probability of this occurring. Okay. So no calculations. Now we're just focusing on interpretation on the test for this part. Okay. All right. Now, having said that, right now when we get into continuous probabilities, we calculated some stuff up here. So we are calculating from the continuous normal distribution. I want you to be able to find the z-score based on a mean and standard deviation. So here, these are the type of questions where I said, okay, these were on the homework. So if I said the mean population, the mean precipitation in a certain city is 99, the standard deviation is 10, what is the probability of getting more than 100 inches of rain in any given year? So those types of questions you will need to be able to answer. Okay. So basically what you need to be able to do is to calculate a z-score from a mean and a standard deviation and another mean that you're comparing to that. So it's this, equals normal, the normal distribution value. So in my case, if the value was 100, the mean was 99, standard deviation is 10, true. So I need to know how to turn that value, which is a probability. I needed to turn that into the answer to my question. So if I said, what is the probability that I will have rainfall of 100 inches or less, then that would be the answer to my question, because this does cumulative from the left side. Okay. So from the left side, 100 inches or less, it's going to be 58.228. But if I said, what's the probability of getting 100 inches or more, I would need to know to subtract that and get from the right side over. Okay. And you could do that here in Excel, or you could do it from the tables. I think it's a little easier to do in Excel. But if you did it from the tables, you would use the formula. Okay. All right. So you do need to know that. That's really the only thing that you need to learn. And I mean, the only real thing that we talked about in Chapter 6. Okay. And so those are the only things on the test there. All right. So Chapter 7, there's not really any computations that went along with Chapter 7. It's all about sampling. So it's making sure that you understand this concept of sampling, that the ideal sample is random, but sometimes that's not practical, and sometimes in very small samples, sometimes randomness doesn't work as well. But it always needs to be probability based. So probability based means that you're not just willy-nilly picking out variables that you think, or values that you think should be part of your sample. Okay. So so you need to go review the steps in the sampling procedure. Then you need to be able to define target population, target area, sampling frame, which are all part of this process. And then you need to be able to recognize different types of probability sampling. What I'm talking about here is stratified, systematic, those sorts of things. They're defined in the book.
That'd be more like visual, like you have like.
Yeah, so there'll be visual or a description, and you can point out which one represents which term. Okay. And again, you have access to the book. So here it might just be, you just go back and look at the book and be familiar with where it is in the book. But I think it would be best to do it. Now, how much time will you have? I'm still going to give you the full time, which in this class technically is 3:40. I know now I'm going past that, but we'll finish up here in a second. So in Chapter 8, you need to define the central limit theorem, which the central limit theorem can be summarized really quickly as the mean of the means is the mean. Why is it important? Well, the distribution of sample means is almost always the normal distribution, and that allows us to utilize the normal distribution when testing whether or not a sample matches a population, even when the underlying distribution isn't necessarily normal. So that's why it's important. So
It allows you to compare non-normal distributions.
Well, it basically allows you to almost any numerical data you can test with. You can test using. You can test it using using these things and derive a confidence interval using the z-tables or the t-tables. Okay. All right. So you should understand what a confidence interval is and what affects its width. So here, I'm only going to ask you to calculate simple confidence intervals that where I give you a mean, where I give you a set of values or a mean or a total and a proportion, no stratified examples. I'm also not going to ask you to ever use the finite population correction factor on the test. So, we're talking about pretty simple formulas for each of these values. You can use Excel, or you can just calculate them out by hand because it's pretty simple. But basically, you need to know that you're going to calculate the width of half the width of the confidence interval, and it's going to be plus or minus that. Okay. So what does affect its width? Well, how does sample size affect the width of the confidence interval? Well, as sample size increases, the width of the confidence interval decreases. Everything else remaining equal. How does the standard error affect the confidence interval? As standard error increases, then your confidence interval is going to increase. Okay, because you're getting, it's the denominator on the equation.
So it's inverse with the sample size and the confidence interval.
Right.
And then it's the same when you do you said the standard error.
Mm-hmm. Yeah. All right, chapter 10. So here is, this should be chapter 9. Chapter 10 is what we're going to over today. I messed up. This is chapter 9. I'll fix that. But before I do fix it, this is chapter 9. And chapter 10 is not on the test. But you do need to be able to make a correct decision. So, in other words, if I give you a hypothesis test, if I give you a hypothesis test, and you go through the steps, and you don't have to actually do any calculations for this. But if I give you a p-value, you need to know what that p-value means for accepting or rejecting the null hypothesis. And you need to be able to state the null hypothesis and the alternative hypothesis. Okay? So you don't need to calculate anything. There's no calculations on this test. Now the final, you'll actually calculate it, but you'll just be using software to calculate it. So
you'll tell us what alpha we want, like how confident we want to be.
I may not tell you the alpha. I may tell you the confidence level.
Yeah, it's like 95%.
Right, and so you'll need to figure that out. But I will give you the p-value, and so you don't actually have to calculate that out. You'll be given the p-value for the result. So you're just taking p-values and comparing them to you're gonna have to calculate alpha yourself, because if I give you the confidence level, you need to calculate alpha, and so alpha is really easy to calculate. It's either 1 minus the confidence value, or it's 1 minus the confidence value, and you divide that by 2, depending on whether it's one-tailed or two-tailed.
And you'll tell us if it's one-tailed or two-tailed, or
yes.
We'll figure that out.
Well, I might not tell you if it's one-tailed or two-tailed, but in the statement, you'll be asked to test whether or not this is greater than or less than this. See what I'm saying?
Different, and then that'll
or is different. So that's going to be your clue. If it says greater than, less than, or different, it's going to be your clue as to whether or not it's confidence. And of course, you know that there are going to be examples where it matters whether it's one-tailed or two-tailed. So if there weren't, then we wouldn't be testing that particular piece of information. Okay. All right. So I'll re-upload that. Does anybody have any questions about the test?
Do we have to take it in here?
Okay, so on Hattiesburg campus, if you all decide to take it somewhere else, so I want to be able to make sure that you're not like working together, right?
Oh, okay. Yeah.
So if you all decide to take it in the other room, or if only one of you wants to take it in the other room, that's fine. But
I was just asking. I was just curious. It's okay. I don't really care either way.
Right.
'Cause I
So
mean-
it's not technically a take-home test. It's something to be worked on individually, but
Yeah.
and it is to be taken in the allotted time.
Okay.
I'll have to go
just
back
take
and
it.
make sure that there's not some exceptions to that. But yeah, it's to be taken in the allotted time, and it's to be worked on independently. So they're,
I mean,
yeah.
I think it's just best, I guess, to take it here. I mean, it's not. I mean, I'll be here anyway, so it's not like it's a big deal.
Okay, great.
So is it going to
That's
be,
what I would prefer. But.
it's going to be through Canvas, it's not like a written, like, physical paper test?
In the past, I've had you write it down, but I could, that's maybe a good idea. I could have it all digital. I mean, that'd be easy to do.
I mean, you could also set it to close at the end of the test. Or, when the time is up, it will just automatically close.
Yeah. Well, I'm not going to be like a super stickler about the time period. So, like, I do want to, be gone by a certain period of time. And it wouldn't be fair to, the other students that do have obligations. Like, some of them at Hattiesburg have already left. So, yeah. But, yeah, I think that's a good idea, though, to put it up on Canvas. So that would mean you wouldn't have to print out anything, too.
Yeah.
That might be easier. So, yeah, I can do that. So you just fill it out.
It'll be quick
Is there a
get
way
back
to
you.
make a question and answer on
Yeah,
Canvas?
as far as I know, at least from all these different tests I've taken, you can have like an essay question, you can have a true false, you can have multiple choice, you can have a calculation, you can have a,
Like,
Okay. Well, I don't know anything about that interface, but I will try to get my test in there.
Worst comes to worst, just send us a Word document. We'll send it back to you.
Yes.
Yeah.
And you can upload the Word document.
Okay.
Yeah, that'll work too. Okay. Any other questions?
Nope. And if we have any questions, we can shoot you an email or see you tomorrow.
Yes, I'll be here tomorrow. Tomorrow, though, I won't get here till closer to class, but I'll be willing to stay after class. I know you're not all in my class tomorrow, but what I'm trying to say is if you want to come ask me questions, that class usually gets out a little bit later than this class, like 4:15. Of course, I think tomorrow it probably won't because we're just doing a test review in that class too. So you come by around 4, I can answer questions if you need.